I'm going live. Just putting the link there. Now, have you gone through that link? What's that term is rent exam not declared? Then do this. You see that?
No, I didn't see that.
Okay. So let's continue with the SQL quickly. Have you got the link?
Yeah.
Yeah. So maybe you want to open that and start doing it from where we left.
Okay.
Let's spend around 20 minutes. So like by 6:30 we should finish that.
We will hear queries with expressions.
Sorry?
We were on this lesson.
Okay.
Should I read it?
Yeah.
In addition to querying and referencing raw column data with SQL, you can also use expressions to write more complex logic on column values in a query. These expressions can use mathematical and string functions along with basic arithmetic to transform values when the query is executed, as shown in this physics example.
Mhm.
Select particle speed divided by 2 as half particle speed. Each database has its own supported set of mathematical string and date functions that can be used in a query, which you can find in their own respective docs. The use of expressions can save time and extra post processing of the result data, but can also make the query harder to read. So, we recommend that when expressions are used in the select part of the query, that they are also given descriptive alias using the as keyword.
Yeah.
In addition to expressions, regular columns and even tables can also have aliases to make them easier to reference in the output and as a part of simplifying more complex queries.
Okay. Let's try that.
All movies and their combined sales, so title,
Yep. Domestic sales plus international sales as. Let's give a space between the plus. Do we need to join? Just thinking. Hold on. List all the movies. Yes, we need to join. That's right. Let's give a tab before on. Box office dot movie ID.
they want it in millions.
Millions.
So
How do you calculate million?
we'll divide it.
Put the number into million.
Okay. List all movies and their ratings in percent.
Divided by what? 100,000?
This is 1 million.
0, 10, 100, 1,000, 10,000, lakh, 10 lakh, 10 lakh. Okay, fine. List all the movies and the ratings in percentage. So title, comma, rating. So rating is out of what? Out of 10, right? So
Yeah,
rating divided
into
by
10.
rating divided by 100 into 10. Wait, rating divided by 10 into 100.
Yeah, so that's into 10, right?
Yeah, I think this is also fine. Wait, into 10. I don't think this will work, will it?
Yeah, it
I don't
works.
think it will work. What's 8.2 into 10?
82.
8.2 into 10. Yeah, 10 into 100. Yep, that's fine.
List all movies that were released on even number years. For this, we don't need to join, I think.
We need where, I think. Where year modulus 2 equals 0. Hmm.
Queries with aggregates. In
Mhm.
addition to the simple expressions that we introduced last lesson, SQL also supports the use of aggregate expressions or functions that allow you to summarize information about a group of rows of data. With the Pixar database that you've been using, aggregate functions can be used to answer questions like how many movies has Pixar produced or what is the highest grossing Pixar film each year.
Mhm. So what does the aggregate
Without,
function do?
um, I think things like max or average.
Summarize the information about the group of rows of data. Okay.
Without a specified grouping, each aggregate function is going to run on the whole set of result rows and return a single value. Unlike normal expressions, giving your aggregate functions an alias ensures that the results will be easier to read and process.
Okay, so what they're saying is that it's basically going to take all the records for that particular value and it's going to run onto that. Correct?
Yeah,
Like for example, if I do count title, it's going to count all the number of records for that particular one. Max means like what's the maximum?
yeah.
Okay.
And this
Count.
count, min, max, average, sum.
Just read for a few of them.
Okay. Count is used to count the number of rows in the group if no column name is specified. Otherwise, count the number of rows in the group with non-none values in the specified column. Min finds the smallest numerical value in the specified column for all rows in the group. Max finds the largest numerical value in the specified column for all rows in the group. Average finds the average numerical value in the specified column for all rows in the group. Sum finds the sum of all numerical values in the specified column for all the rows. Grouped aggregate functions. In addition to aggregating across all the rows, you can instead apply the aggregate functions to individual groups of data within that group. That is box office sales for comedies versus action movies. This would then create as many results as there are unique groups defined as by the group by clause. The group by clause works by grouping rows that have the same value in the column specified.
Find the longest time that has an employee. Find the longest time that an employee has been at the studio. So find years. I think max years.
Yeah.
You may want to put the employee name also. Name. Enter. Enter. Yeah. Find each role. For each role, find the average number of years employed by the employees in that role. So I think we have to group by in this case, right? So
Yeah.
number of years for each role, average number of years. Uh,
Group by role.
okay. Can you put name also? I mean, can you put name also?
Okay. But name, won't there be several names with the same
Sorry.
role? There will be
When you
several
have a.
names, right?
Mhm. Okay, so I just want to
With the
understand
same
taking a.
role.
Okay, I just want to understand taking a moment here. So what this is done is, of course, I understand the average number of years that role has been, uh, person has been in that role, and I think why can't the name be here? I think name can be here because it's saying that one person for how long they have been into that particular role. So I think name can be put here. It's fine.
No, it's average number of
Hmm.
years employed by employees in that role.
Are we
So
getting a
won't there be
different result if
several
we.
artists?
For each role,
That
find the number of years employed by the employees in that role. For each employee, are you talking about each employee?
no, for each role.
Okay.
So we have several employees for the same role. We're
Hmm.
finding the average of that.
Hmm. When we did group by, what did that do?
Then it groups all the rows with the same role.
Remove the name. Mhm. So when you said grouped it, you mean um did it? Is it giving like a remove the average? Let me see what happens if we grouping by role. Okay, so what's happening now? What is it actually doing when we are grouping by role? So it's putting the that particular role once, and is it combining uh, some data for that? What is it actually doing at this point?
For years employed,
Mm-hmm.
I don't know what it's doing here.
No, no, no.
It's
I'm
just doing
asking
one
you.
of the values.
When we group by role, right?
Yeah.
So what did that do to the data? How did that change the data? Remove the group by role once, just that line. Okay, so this is actually giving us. So let's take an example of engineers. So engineers giving me the list of all the years employed. Okay, and now when we do group by, what is it? What is doing to the data now? It's giving only one. So does that mean uh, wherever engineers have a value uh, as years employed as one, it's going to just use those value. What is it doing? I'm just trying to understand that. This group by role.
No, it's grouping all the rows that have role as engineer.
Okay. But how is it placing the years employed against them? What's the logic of?
I don't know.
Okay. Okay.
Is it same as average?
No.
No.
No. That's what I try to understand. What did it do to the data next to it, which is the years when we grouped by? Okay, no problem. Just carry on.
Find the total number of employee years worked in each building. So we have to use sum, I think.
Mm-hmm.
Select
Years employed.
building.
I think you have to use group by year.
Yeah.
Hmm. Now check. Wait, wait. Go back.
Check
The
what?
query is lost, right?
Yeah.
Okay. Now we have to do all of the. Can you press forward? Try pressing forward.
Forward, forward.
Yeah, that's fine.
To go. Okay.
Let's, let's continue from here. Let me read this. On our queries are getting fairly complex, but we nearly introduce all the important parts of select query. One thing you might have noticed that if a group by clause is executed after where clause, which filters the rows which are to be grouped, then how exactly do we filter the grouped rows? Luckily, SQL allows us to do that by additionally having clause, which is used to specifically with group by clause to allow us to filter grouped rows from the result set. The having clause constraints are written the same way as where clause constraints and are applied to the group rows. With our example, this might not seem like a particularly useful construct, but if you have imagine data with millions of rows with different properties, being able to apply additional constraint is often necessary to quickly make sense of the data. If you aren't using group by clause, a simple where clause will suffice. For this exercise, we are going to dig deeper into employee. Think about different clauses you might want to apply for each task. Find the number of artists in the studio without a having clause. So, number of artists. Um, so, yeah, so count, role, where, where role equals artist. Yeah. Find the number of employees of each role in the studio. So select
Count
employee.
name.
Yeah, but before that, we have to put role. Yeah. Remove the where clause. and group by role. Yeah.
Find the total number of years employed by all engineers.
Okay, so sum years and remove the role.
We still have to use group by one to
Yeah,
group
years
the years.
employed. Years employed, I think. By engineers, it's saying. So we have to, yeah, we have to use where.
Or having after group by.
Okay. Hmm. So they're saying that you can use either where or you can use having, right? The only
Yes.
difference is that if you're using where, then it has to be used before group by, I guess, and
Yeah.
having comes after group by. Can you try removing the having and using where clause before group by? No, just remove the last line. That still works, right? Hmm.
Yeah.
No, wait. Yeah, that's fine. That works. Okay, let's stop here on this part. Let's go on to the theory.
Okay.
Which topic were we on? We were supposed to start from graphs, right?
Yeah.
So graphs is a collection of vertices and edges. So vertices is the node, I believe, and edges is that line, correct?
Yeah.
Okay. The set of vertices is always non-empty. Edges represent ordered or unordered pairs of vertices which are directly connected to each other. If the pair of vertices are unordered, it means that edge indicates that V1 is directly connected to V2 and vice versa. If the pairs of vertices are ordered, it means the edge indicates that V1 is directly connected to V2. Um, V2 is directly connected to V1 if the edge present. Okay. Minimum cost spanning tree. A spanning tree is a subset of a unidirected graph that has all the vertices connected by the minimum number of edges. So basically, the rule is that all the vertices needs to be connected by the minimum number of edges. And of course, it shouldn't form a kind of a circle like cycle. Minimum spanning tree is a subset of edges of a connected weighted unidirected graph that connects all the vertices together with the minimum possible total edge weight. What's the difference between it's the same thing? Subset of edges, subset of graph, connected weighted graph connects all the vertices together with the minimum possible total edge weight. To derive an MST minimum spanning tree, following algorithms can be used. Prim's algorithm, Kruskal's algorithm. Start with the okay. Wait a second. Talking about that, then why did we start with the Shikshra? We should start with Kruskal's. Okay, so Kruskal's algorithm is used to find the minimum spanning tree for a connected weighted graph. The main target of the algorithm is to find the subset of edges using which we can traverse every vertex of the graph. First, sort all the edges from low weight to high. Now, take the edge with the lowest weight and add it to the spanning tree. If the edge to be added creates a cycle, then reject it. First, sort all the edges from the low weight to high. Now, take the edge with the lowest weight and add it to the spanning tree. If the edge to be added creates a cycle, then reject it. Continue to add the edge until we reach all the vertices and a minimum spanning tree is created. Time complexity is OE log E or OV log V. E is the number of edges, V is the number of vertices. Applications are used to lay out electrical wiring among cities and can be used to lay down LAN connections. Now let's take a look at an example. So this is the connected weighted graph. First, we're going to place all of these edges and their weight, and then we're going to sort them in an ascending order, and then start placing them one by one. The moment we see that it's forming a cycle, we reject that particular edge, and then we continue until all of them are covered, and then we add the total of them. So first the edge is AB and the weight is 1. So to the MST, add the edge DE, weight is 2, and it's not creating a cycle and so on and so forth. Dijkstra's algorithm, a single source shortest path algorithm. Here single source means that only one source is given and we find the shortest path from the source to all the nodes. So basically, in this algorithm, we have to find the shortest path from the source to all the nodes. And in the Pascal's algorithm, we have to find the minimum spanning tree for connected weighted graph, which means find the subset of edges using which we can traverse every vertex of the graph. Okay. Uh, Applications are to find the shortest path in social networking application, in telephone network, to find the location in a map. So first we choose a source node, assign 0 and assign infinity path values to all other nodes like this. Then start from the source node, update the adjacent nodes with the minimum weight distance from the source node. So minimum weight for these ones were 4 and 4, so we updated these guys, these nodes. In this step, the adjacent nodes are 4 weights apart from the first node, so we update the values 4 and 4. Then traverse to the next adjacent unvisited node that has minimum distance from the source node. So if you start from here, unvisited are either of this, because if this was 3, then we would have visited this one first, but since both are the same, we can visit any of them. So let's start with this one. So we visit this one, and then all the adjacent nodes we have to update their weight. In this case, the adjacent node is 4 and 0. So sorry, this one and this one. This is already updated, and before updating this one, we have to calculate uh, the the edge basically. Sorry, the weight if it's larger or smaller. So let's see. Then update the weight of all next one coming to the source node. Keeping in mind that the calculation is done considering we traverse from the source node through the currently visit node. So we have to traverse to this one through this. So 4 plus 2 is 6, and this is 4. So to reach this node from the source node, there are two ways. One to go from here to here. Another one is to go from here to here. Of course, this is smaller, so we're not going to change anything. Is if this was less, let's say this was 1 and 3, sorry, 1 and 2, so 2 plus 1 is 3, then would have updated that, but because this one is smaller, we don't make any change, and then we just follow the same rule until we have visited all the nodes. If the shortest distance from the source node to the those of adjacent node is less during traversal, don't update the node. Repeat this process until all nodes are visited. We have search algorithms. First is linear search. So linear search, we start from the first element, go up until the last element, until the match is found. It's a sequential search algorithm, starts at one end, goes through each element of the list until the desired element is found. Otherwise, the search continues till the end of the data set. It is the easiest searching algorithm. Start from the leftmost element of array and one by one compare x with each element of the array. If x matches with the element, return the index, else return -1. Binary search with example. So binary search is a searching algorithm used in a sorted array by repeatedly dividing the search interval in half. The idea of the binary search is to use information that array is sorted and reduce the time complexity to O log n. Okay, so it's a searching algorithm used in sorted array by repeatedly dividing the search interval into half. So we know that the array is sorted, and we aim to reduce the time complexity to O log n. Algorithm is that you begin with the mid element of the whole array as a search key. Then you check if a match is found, you return that element. If not, then you check if that uh, the the item you're trying to search, is it less than or greater than the mid element. If it is less than the mid element, then you basically divide the interval into the left half, like you extract the left half and ignore the right half, and vice versa if it's greater. And then you continue your search in the same manner. If the value of the search is equal to the item, and return the index, or if the value of the item to be searched is less than the middle element of the interval, decrease the interval into left half, otherwise decrease it to the right half. Repeatedly check for the second point from the second point until the value is found or the interval is empty. So this is an example. Now we talk about the sorting algorithms. So in sorting algorithm, we have insertion sort, bubble sort, quick sort, heap sort, two-way merge sort. Am I missing anyone? One more. Topological sorting. Insertion sort. So I think this is an example where uh, you know we have different number of cards, and then we have to sort it out. Programmatically, what we do is we create two lists. One contains the unsorted list. Second one will contain the sorted list. And we first start by placing the first element into the sorted list, and then we start moving elements from the unsorted list to the sorted list. And in the sorted list, we start comparing the element. If the element is greater, let's see what's the condition there. Okay, this is a naturally occurring sorting method exemplified by a card player arranging the cards dealt to him. He picks up the card as they are dealt and inserts them into the required position. Thus, at every step, we insert an item into its proper place in an orderly sorted list. To find the correct position, search the list till an item is just greater than. Okay, this is the thing. Item just greater than the target is found. So we have to search until the item which is just greater than the one we want to insert is found. And once we find that, we start shifting the all the items from that point towards right, and then we place the our item over there, because that creates a hole, and we place the item in the hole. Iterate from an item array 1 to array n, which is from first to last. Compare the current element to its predecessor. If the key element is smaller than its predecessor compared to the elements before, move the greater elements one position up to make space for the swapped element. So mark the first element as sorted. For each unsorted element, extract the element if j is less than last sorted index down to 1. For j last sorted index down to 1, current element j greater than x, then move the sorted element to the right by 1, break the loop, insert the element here. Bubble sort. I think in bubble sort, we consistently check the adjacent elements, and if they're not in order, we swap them. So in bubble sort, we repeatedly swap the adjacent elements if they're not in order. This algorithm is not suitable for large data sets as average and worst case time complexity is quite high. Run algorithm, the bubble sort in ascending order. Begin, read the array, the length of the array. Loop from the second element to the last element. For I equals 1 to n, loop from the last element to the current element. So in the first loop, in the outer loop, we loop from the second element to the last element, and from the inner loop, we loop from the last to the current. And for j equals n minus 1 to I, and swap the adjacent elements if they're not in order. If array j minus 1 is greater than array j, then swap array j with array j minus 1. Quick sort. So the basis of quick sort is to divide. The basis of quick sort is the divide and conquer strategy. Divide the problem list to be sorted into sub-problem, sub-list until the solved sub-problem, which is sorted sub-lists, are found. Time complexity is O n into log n. Partition around 70. How are they dividing? 10, 30, 40, and 50. And then 1980. Partition around 50. Choose a pivot and move it to the end of the array. Then start comparing the element greater than the pivot and smaller than the pivot, and then swap it, I believe. The left insert from the right. Insert from the left that is larger than the okay, item from the left that is larger than pivot, and item from the right that is smaller from the pivot, and we swap those elements. Okay, then again we do the same thing. Item from the left should be larger, item from the right should be smaller. So find the smaller element from the right and larger element from the left, and then swap them. The moment they encounter each other, uh, they've crossed each other, and that means we don't have to, we have to stop doing this. And at this point, yeah, so if item from the left is greater than the item from the right, you stop the swap there. At this point of time, uh, swap item from left with the pivot. Are we choosing another pivot here? Or we're just swapping the item from the left with the pivot.
3.
So are we choosing a pivot? Because here it says swap the item from the left with the pivot. Item from the left was 5. Are we choosing another pivot here? It looks confusing here.
We'll choose a pivot in the next recursion for the subarray.
Okay. Swap item from left with the pivot. Pivot is now in the right place. So the rule is that items to the left should be smaller than the pivot, and items on the right should be larger than the pivot. Repeat the process for the left and right sides. Okay, same thing here. So find the element that's larger, the item on the left, and find the item on the right that is smaller, and then swap them. So we did that. Let's watch that video once again to avoid that confusion.